All right, so let's start this e-learning. So what we're talking about in this chapter is exponential functions and logarithmic functions. Now, what's really important to know about exponential functions and logarithmic functions is that they are inverses of each other. So what I mean by that, or what I like to give an example as, is if I gave you the equation 3x equals 6, and I said, how do you solve this? I know everyone would say, well, divide by 3. Right? The reason we do that is because multiplication, which is going on right here, and division, which we're trying to undo it with, are inverses of each other. So when you see something that says, find the inverse of this, and it's a log, the inverse is an exponential function. When you see something that's an exponential function and it says, find the inverse of this, the inverse is a log. If you know those things, this lesson's pretty easy. So, speaking of, let's get started with this lesson. So first off, let me get this to go away. There we go. What I just said, the functions are inverses of each other. So if I wanted to see what a log looked like, which you guys saw in Algebra 2, we have log base b of y is equal to x. If I wanted to rewrite this an exponential function, this right here is called the base. If you look over here, if I wanted to write it as an exponential function, this is called the base. Another important thing to know is that logs are exponents. So whatever a log is equal to, x in this case, is an exponent. This right here, this part right here, that y part is called the argument. So whenever you hear me say argument, the argument, what am I talking about? That's the of part. That's the part that's after the log, base, whatever. So it's always equal to the argument. Okay. Next, let's talk about common logarithms. So the common logarithm looks like so. If you look at it, it has no base. And it's not that it has a base of 0 and there's no base. It's just that if it's not written there, the base is 10. So if you looked at your calculator and you see the log button there, that's common log. It's common log with a base of 10. The next important log to know is natural log. Okay, a lot of people call this ln. It's actually called natural log, so I'll try to not say ln, but that's what it means. Natural log is the same thing as log base e. So if you see natural log and you're working with an equation that you have to rewrite, maybe the inverse of, let's say, a lot of people like to rewrite it as log base e first, so that it's like every other problem we've been doing. So that's the basics we need to know before we get started. So first off, we are going to start with rewriting each as an exponential function. So one thing that I want you to know is that we're just rewriting it. We're not rewriting it and then doing anything else with it. If there's other things that are improper about it, we're just leaving it for now because it just says rewrite. All right, so this first one right here, this one, if you need to read it so that you get this easier later, it says y equals log base 2 of x. So the base is 2, so that's what I'm going to start off by writing. The base is 2. Logarithms are exponents. So whatever your log is equal to, that's your exponent. And it's always going to be equal to whatever the argument is. So it's 2 to the y equals x. That's how you rewrite this one. Next one, same idea. 5, which is the base, to your exponent, which is what your log is equal to your argument. Next one here, go ahead and try that one on your own. You can pause the video and do that. All right, if you tried it, you should have 9 to the 1/2 is equal to 3. Next one you can try on your own. It is one that's a little tricky, but still, I gave you the clue of what you can change natural log to. If you had a chance to pause the video and try it on your own, this is what you should get. So if you rewrite this natural log as log base e, remember this and this are the same thing. You still have this e right here equals 1. So now if I wanted to rewrite this in exponential form, my base is e, my exponent is 1, equals my argument, which is e. So e to the first equals e. When I'm done, it still makes sense. If you look back here, c still makes sense. 9 to the 1/2 power is 3. 1/2 power is the same thing as square root. 5 squared is 25. Still makes sense. Last one here in this section, go ahead and pause the video, try it on your own. What I have students do is that I have them put a 10 right here to help them. 10 to the third power equals 1,000. Once again, makes sense with the problem we're working with. All right, let's move on to the next section. So this is writing the exponential function as a logarithm. Okay, so first and foremost, it has to have log in it. So I write down log right away. Now I need my base. Okay, so base is still the base of the exponential function, so 2. I need my argument. Remember, it's equal to your argument, so of 8 is equal to 3. And remember, logs are exponents, so your exponent should be written on the other side of the equation as the log. All right, this one right here, log base 3 of y equals my exponent, x. Logs are exponents. Go ahead and try the next two, see how you do. Pause the video. All right, if you gave yourself a chance to do that, you have log base 16 of 1/4 equals negative 1/2. This one right here, log base root 5 of 25 equals 4. All right, so that's rewriting. Now we're going to find the exact value, okay? So realize a lot of times what I'll see students do here, because this is how I first start teaching, is saying you want to know what this is. So this is your unknown, this is x. So we're going to find this value by rewriting. So I also tell people that if you're ever stuck, rewrite it. If you're stuck with a logarithm, you don't know what to do, rewrite it as an exponential function and you might know. So this one would be 4 to what power gives me 16? Answer 2. You don't have to put x equals 2 because you put the x there. It wasn't there originally. This next one right here, using the same idea, what is this? What is the unknown? So I'm going to rewrite it in exponential form. My base is 25. My exponent is x equals 5. So it's saying 25 to what power gives me 5. Now you realize that the number got smaller. If the number gets smaller, that means your exponent is a fraction, not a negative number, a fraction. So I say to myself, well, how do I get a 25 to be a 5? I square root. What's square root? The same thing as what power is that? That's the 1/2 power. All right, next here, same idea. I have 4 to what power gives me 1/4. So number got smaller again, but this time it became a fraction. If you look, that number, which is 4, went to the denominator. To get a number to go to the denominator, we need negative exponents. It stayed the same value. It didn't get squared or cubed or anything like that. So I know it's a first power, but since it went to the denominator, it's -1. Next one right here. Once again, you can rewrite it as log base e, or just even throw an e in right there as the base so you know it's there. And then once again, this is what you're looking for. You're looking for what is this equal to. So if I rewrote it, I would have e, that base that I wrote in, to my exponent, which is x, equals my argument, e to the 5th. So this is really just a matching game right here. The base is already the same, so these have to be the same. X equals 5. Go ahead and pause the video and try the last one. All right, you should have gotten root 7 to the x equals 49. All right, so I have to ask myself on this one, what do I do to a root 7 to get to be 49? So if I said square it, it would just become 7. But then I have to square 7 to get me the 49. So squaring a square is the same thing as the 4th power. All right, so next what we'll talk about is finding the inverse. So this is where the beginning of the lesson comes in really handy. And when I say the beginning, I mean me saying that logarithms and exponential functions are inverses. So when you look at this problem right here and it says find the inverse of this log, the answer is an exponential function. It should look like an exponential function, like 2 to the 5th equals y, or that's not a good one. 2 to the x equals y, or 8 to the x minus 2 equals y, something like that, or y equals 2 to the x. Those are all exponential functions. So we all know the first step of finding an inverse. The first step of finding an inverse is switching x and y. So we have x equals log base 4 of y. Okay, so now I'm going to switch to that page that I had blank up here because I actually want to write down my steps here so that you can see them. You're going to switch x and y. You are going to isolate the argument. I don't know if there's another E in argument, so we're just going to spell it my way. Isolate the argument, and then third step is rewrite as an exponential function. Okay, so rewrite as exponential function. So this part right here, isolate the argument. Remember what the argument is. It's what's next to the log base whatever. So for example, I'm going to give you two examples of a non-isolated argument and an isolated argument. So if you had y equals, actually these would already be switched x and y. So let's do x equals log base 3 of y versus x equals log base 3 of y plus 3 versus x equals log base 3 of y plus 3. In two of these, the argument is isolated. It's by itself. This example, the argument's by itself. This example, because it's all tucked in with that parentheses, the argument's by itself. In this example, the argument is not by itself. So to get the argument by itself, the first thing I would have to do is subtract 3 from both sides. X minus 3 equals log base 3 of y. Now the argument is isolated, and you can move on to the next step, which is rewrite as an exponential function. So let's go ahead and do that. We switched x and y. I asked myself, is my argument isolated? Yes. So if the answer is yes, I can just rewrite an exponential form. So I start with my base. What's my base? 4. Now I need my exponent. What's my exponent? It's what my log's equal to. So to the x power equals, and then it's always equal to your argument, y. The last thing that we want to do is that, where did the y come from, right? Like we changed it from f of x, and this is the inverse. So just like last semester, we're going to say f inverse of x is equal to 4 to the x. And now we can see that we have our exponential function. All right, next one. We're going to start by switching x and y. So we have x equals, as soon as I see natural log and I'm doing exponential or rewriting as exponential functions inverses, I switch natural log to log base e. It's just, I know I'm going to end up having to do it, so I might as well. And you can see that I forgot to change that to a y, so now I will do that. All right, so now I ask myself, is my argument isolated? Yes, it is. So I can rewrite in exponential form. My base is e, my exponent is x, equals my argument's y. Once again, I want to change that to y inverse because this started off as y. So y inverse equals e to the x. If you go from here to here, there's nothing wrong with that. All right, excuse me. Last one, switch x and y. Remember, this is y, this is x. So I'm going to do x equals, I'm going to change natural log to log base e, y plus 3 minus 2. All right, so now I'm going to ask myself, is my log isolated? The y plus 3 isn't a problem, it's the minus 2. So it's not, so I'm going to add 2 to both sides. X plus 2 equals log base e of y plus 3. Now I can ask myself, is my logarithm isolated? Yes, it is, because it's just a y plus 3 here. And it's in parentheses, it's tucked in there. It's not, the 3 is not floating on the end. All right, so let's go ahead and rewrite an exponential form. My base is e. My exponent is x plus 2 equals my argument, y plus 3. So this one's almost done, but notice that the equation has to be solved for y. So the very last thing I'm going to do is subtract 3 from both sides. And now I can write my final answer. Instead of writing y equals, I'll skip that step, and I'm going to say g inverse of x equals e to the x plus 2, which is my exponent, and then minus 3. And there's my final answer. All right, so the last thing that we have to do before graphing, and I'm going to go quickly through graphing, is find the inverse of the exponential function. So ask yourself first, what's the inverse of an exponential function? Logarithms. So same steps here. You are going to switch x and y, and then you are going to rewrite as a logarithm. Okay, so switch x and y. X equals 3 to the y. Rewrite as a logarithm. And this would be as long as this is isolated, which if there was like a plus 6, then it would have to subtract 6 from both sides. So as long as your base is isolated, which neither of these examples, the base is not isolated. All right, so I'm going to rewrite as a logarithm. So I'm going to write down the log. My base is 3. Of my argument, which is x, is equal to, logs are exponents, y. And then once again, just rewrite it as f inverse of x, because that's what the original was titled, f of x, log base 3 of x. Go ahead and try the last one on your own by pausing the video. All right, you should have gotten x equals 1/2 to the y power. It's isolated, so I can rewrite as a log. Log base 1/2 of x equals, and then instead of putting equals y, I'm going to automatically change it to y inverse. And notice I wrote it on the left-hand side just because that's what we want to see. We want to see y on the left-hand side. But if it's on the right-hand side, it's also correct. All right, last but not least, we have graphing exponential functions and stating the domain, range, asymptote, and end behavior. So it says, given the function g of x equals 1/2 to the x power, graph the function using at least 4 points. So, and then it says this is an example of exponential blank. So we're looking for whether it's exponential growth or decay. So we'll see what the graph looks like before we decide that. So what I'm going to do is I'm going to plug in the values -1, -2, 0, 1, and 2, just so I can get an idea of what this looks like here. All right, so let's start with -1. So 1/2 to the -1 power. Remember, a negative exponent you bring to, when you have a fraction, you bring it to each of the numerator and the denominator. But then also negative exponents make them change places. So this becomes 2/1, which is 2. 1/2 to the -2 power, same thing, you're going to square both and then change their places. So that's 4/1, 4. Plug in 0, anything to the 0 power is 1. Plug in 1, I get a 1/2. Plug in 2, I get a 1/4. And now I can graph these 5 points that I just got. So -1, 2. I don't know why I put -1, -2 there. That really bothers me. So I'm going to switch them because they're not in numerical order. That's really weird. -2, -1, and this is 4, 2. Okay, -1, 2, -2, 4, 0, 1, 1/2, and 2/4. So now I have to bring this up. I have to say, like, if I plugged in 80 billion, am I ever going to touch or cross that x-axis? So what you have to realize is that your numbers are getting smaller and smaller and smaller and smaller and smaller to where they're so close to 0, but they're never going to become 0. We know what that means. That means that there's an asymptote on the x-axis right here at y equals 0. So our graph right here is going to look like so. And it's going to get closer and closer and closer and closer to our x-axis. All right, so if you look from left to right, our numbers are getting smaller and smaller and smaller. So this is an example of exponential decay. The domain of that pink function right there, all real numbers. It goes from an arrow to an arrow. The range of that pink function right there, if you look at them, the smallest y value is some number very close to 0, but not 0. So what I'm going to say is that it's 0, 2, but not including 0. And then it goes forever, infinity. There's an asymptote at y equals 0. And then for our end behavior, remember we write end behavior in limit notation. So the limit as x approaches -infinity of our function, which name is g of x, is equal to So if we look at the left-hand side behavior of our graph, as our x values are getting smaller, our y values are getting bigger. So they are approaching infinity. Limit as x approaches positive infinity of the function g of x is equal to, and as you look right, our values are getting closer and closer to 0, and they're leveling off there. They're never going to hit 0, but remember, a limit is what a function approaches but never necessarily reaches. Okay, last is growth. I obviously gave that away, but it's a base of 2 versus a base of 1/2. Go ahead and fill in your table on your own here. You can do -2, -1, 0, 1, and 2 again. So pause the video and fill that in. All right, you should have gotten 1/4, 1/2, 1, 2, 4. So go ahead and graph that. -2, 1/4, -1/2, 0, 1, 1, 2, 2, 4. Once again, if you look to the left, if you look at the values going to the left, they're going to get closer and closer and closer to 0, but they're never going to reach 0. So I'm going to go ahead and put an asymptote there. And then I'll go ahead and make the rest of my graph, the rest of the values that go in line with it, and get really close to the x-axis there, but never touch it. This is an example of exponential growth. If you look from the left to the right, the values are skyrocketing here. All right, so domain, once again, arrow to an arrow. Go ahead and fill this part out yourself. Pause the video again, make sure you're able to get it. All right, so if you did that, you should have -infinity to infinity. Our range, 0 to infinity. Our asymptote, y equals 0. This is a parentheses, by the way. It looked kind of brackety when I was looking at it. End behavior, the limit, there's not a lot of room for that. The limit as x approaches -infinity of our function, which is named f of x, is, if you look as your x values are getting smaller, what's happening to your y values, they're leveling off at 0. And then the limit as x approaches positive infinity of our function, which is f of x. As you look at your x values, or to the right, as your x values get bigger, our values are getting bigger and bigger and bigger, so infinity. Next it says, what is the equation of the inverse, okay, for this problem? So if you look right here, here's the original. This is just extra practice here. So the inverse of an exponential function is a logarithm. So let's just get that logarithm. We'll put x equals 2 to the y power. Now, it's a logarithm, like we said, so I'm going to rewrite it. Log base 2 of x, I'll put the equals over here because I know I'm almost done. And then instead of writing y, I'm going to write f inverse. So there is the inverse. So filling this in really quickly, what we have to realize. If you look at f of x, the asymptote is y equals 0. The domain, all real numbers. The range, 0 but not including 0 to infinity. Remember what inverses are. We know the first step to finding an inverse is switching x and y. So if I want to know what the asymptote of a logarithm, keep in mind it has no transformations done like this one. The asymptote is at x equals 0 because I have to switch the x and y. This is x, this is y. I have to switch the x and y's. So 0 to infinity, -infinity to positive infinity. What's the end behavior? Once again, you just switch